The speaker is Martin White. He's going to speak on nonlinear structure in the universe.
Okay. So I was asked by the organizers to talk about nonlinear structure in the universe, and so one of the first things that arises when you start talking about how one deals with nonlinearity is the fact that you actually have very, very few options. So in some ways that makes it easy to talk about, I guess. So beyond some certain scale, it's going to be true that linear perturbation theory, which I guess you're going to hear about a little bit later today, begins to break down. So the first question one could ask is what is the definition of this nonlinear scale? It's sort of an interesting question. But suppose I do go beyond this nonlinear scale, then at some point I have to decide what I'm going to do beyond linear perturbation theory, and we really only have essentially three kinds of techniques. You can try some sort of analytical model which exactly solves a problem usually not of interest, but then at least you've got an exact solution of a nonlinear problem, if not the one you cared about. You can talk about perturbation theory, which is what I want to spend today and a little bit of tomorrow, a little bit of my second lecture talking about, or you can do sort of a direct brute force simulation, and I'll talk about that at the end. I want to start by talking a little bit about perturbation theory and its realm of validity, what you might use as a convergence criteria, and so on. But first I want to deal with this question of the nonlinear scale, because you see a lot of different things written in the literature about this. So the notational scheme I'm going to use throughout this is the fractional density contrast, so rho minus rho bar divided by rho bar, where this is the mean density of the universe, is delta of x. My Fourier transform convention is sort of the standard one in cosmology, where all of the 2 pi's go under the k's. And that makes my power spectrum look like this, and my dimensionless power spectrum be k cubed p of k over 2 pi squared, just so you know where I put 2 pi's. For most of the age of the universe in sort of log time units like we normally think of, and for many scales, linear perturbation theory is completely valid. You're going to hear about linear perturbation theory in a while. All I'm going to need to know from linear perturbation theory is that the density perturbation at some scale k today looks like some growth factor times some function times the initial power spectrum, or the initial density perturbations, and this factor is known as the transfer function, and this basically encodes the 14 billion years of evolution in the universe, and it basically contains 2 features, one due to a transition from radiation domination to matter domination, and then possibly a second feature if I go to a dark energy dominated universe. And the physics behind this is essentially that structure only grows when matter dominates the energy density of the universe. So if I plot this power spectrum, it scales roughly like k to the first power out here. It rolls over and goes roughly like k to the minus 3 over there. The scales here are set by the density of matter, and these sort of features, these so-called baryon acoustic oscillations, are set both by the baryon density and the matter density. And I'm not going to go into the physics of that in this set of lectures, but I'm sure you'll hear about some of that a little bit later on. If I plot this in dimensionless form by multiplying by k cubed, I get a set of curves that basically increase all the way to the right, and these would eventually flatten out and have only a logarithmic growth at large k. And what's plotted on here is both the linear theory, and you can see these points here are actually the nonlinear theory taken here from an n-body simulation. And then I've divided out this sort of smooth curve here to bring everything down onto a nice linear axis, and you see the same set of points down here, and you see there's an excess of power at small scales where things go nonlinear, and we'll look at this in much more detail as these lectures proceed. And so the question is, where do I basically say nonlinearity sets in? It's clearly pretty linear over here, it's clearly going quite nonlinear over there. What's the right kind of scale to go from one to the other? And there's lots of ways that you see written in the literature. So one way of doing it is to say, well, this dimensionless density contrast is equal to 1. Or if you prefer, a half, or 0.4 is a very common number, and so on and so forth. And so people often talk about that. This is quite dangerous when your dimensionless density function becomes quite flat, because you can imagine, if I have an almost flat function, and I'm trying to say, where does that cross some threshold, then a tiny, tiny change in the amplitude leads to a massive change in the scale at which that crosses that line. And that's led some people to make mistakes in the past, so that's not actually a particularly good definition, although it's a relatively common one. There's one that I'm going to advocate, and we'll see why a little bit later on, and it's if you calculate how far some particle in a simulation or something should have gone, and I just use linear theory, how far should that be displaced, and call that this nonlinear scale, or 1 on a nonlinear wave number if you prefer. And then this calculation just turns out to be doing this simple integral, or calculating the integral of this power spectrum. And this will turn out to be a quantity that we'll see several times as this lecture goes on. This is quite a good definition of nonlinearity, and it's quite well behaved. Perhaps the most exact definition in some sense would be to go and calculate the second order correction, or the third, or whatever you're up to in perturbation theory, and ask when is that second order correction 1% or 10%, depending on how conservative you want to be, of the first order term, right? And that's in some sense the best definition of nonlinearity you can have, except that you've already done all the work to calculate the second order correction, and then at that point you sort of just throw it all away and use that entire calculation, which was 10 times harder than anything else you did, merely as an error, a warning flag. So that's not so nice. So I want to break my discussion of nonlinearity into sort of the two limits: weak nonlinearity and strong nonlinearity, and I'll talk about strong nonlinearity towards the end. So I want to start with weak nonlinearity in cosmological perturbation theory, and this is the idea that, surveys are getting bigger, simulations are getting better, we're learning more and more about the universe, and so there are some realms of questions where the kind of thing we're interested in is I have a very large survey and I'm working on very, very large scales, and things are almost linear, but I want to ask an incredibly precise question, so almost isn't good enough. And so I want to calculate a small correction to something that is quite linear, right? So what I'm dealing with then is sort of weak nonlinearity, where I just want to know what is the correction, and I know it's pretty linear. And that's where some kind of perturbative theory is a good way to approach it. And then, of course, the other set of questions are when things are qualitatively just very nonlinear. And so perturbation theory there might be a bad idea. So perturbation theory is almost, in some ways, completely obvious. You basically just say, let me imagine that I've gone through and I've done a linear perturbation theory calculation to do all of those power spectra and everything else. There's no reason to stop at linear order. I can expand to all orders, so I can write my full density contrast as a piece that is first order in some small quantity, plus a piece that is second order in some small quantity, plus a piece that is third order in some small quantity, and so on, just like you learned, back when you did, I don't know, Taylor's theorem or something. If you want, you could take these terms and do it order by order in that expansion, or you could try and sum some subsets of those terms, and then you can try and figure out whether what you've done in terms of summing this or expanding this is useful, or whether this expansion is in fact converging. And that actually turns out to be much, much harder than doing the expansion itself, and I'll show you some examples of that as we go along. So the problem I want to deal with for now, although it's not the only thing one could do, is to consider only dark matter. So I'm going to neglect other things that happen on small scales like baryonic physics and so on. Not that you absolutely have to do that, but it's going to make our life a lot easier. And I'm going to assume that we're in the single stream limit, and if you don't know what that means, don't worry about it, it doesn't really matter. And if you make these assumptions, then the ideas behind perturbation theory actually go back a long way. They go back a little bit further than some of these references here, but they're first really seen in these papers by Peebles and Juszkiewicz and Goroff and collaborators and so on, going through. This paper by Jane and Birching is extremely nice exposition of how perturbation theory in its standard form is developed, and so that's a good place to go and look. There's a review by Bernardeau and collaborators, which is now getting a little old, and so it doesn't have a lot of what's happened in the last decade or more of perturbation theory, and it's been relatively active as people have taken another look again and said, hey, there's lots of information coming in on large scales that we can measure now. Let's go back and look at perturbation theory again. I'm going to be pulling a lot of plots and so on from this paper by Jordan Carlson and company. He was a graduate student working with me who looked at this just last year, so it's relatively up to date. And so you can find all of these references easy on the web. So if I make those assumptions that I wrote down previously, and I assume for now that the matter density is 1, that's just a technical simplification. It's easy to generalize, but it will make some of the equations easier if I don't do that. Then the equations of motion look like the following. I have a continuity equation, an Euler equation that is sourced by the gradient of some gravitational potential, and a Poisson equation. And these are the equations of fluid behavior, or whatever you want to call it, in the universe. And they're very, very familiar looking equations, and obviously that's comforting. It also means that you can go and borrow, steal, plagiarize, whatever the appropriate term is here, methods and ideas from other fields, and you'll find a huge amount of the perturbation theory literature in cosmology is really lifted directly from perturbation theory literature in particle physics or fluid mechanics, turbulence theory, and so on. And so that's there's a lot of great ideas that other people in other fields have worked out that you can just basically take their paper, cross out their names in crayon, write your own in, and instant fame. The thing to notice about these equations is this quadratic nature of the nonlinearity, by which I mean if you look at where these things are nonlinear, it's in the VV term and the delta V term. There aren't any cubic terms in here, right? This is a very particular kind of nonlinearity that we're dealing with. But these equations are, however, nonlinear, and because they're nonlinear, that means when you start asking what does it mean to solve these questions, you have to take a step back a little bit. We're so used to maybe training from electromagnetism or something. We're so used to the principle of superposition and the idea that once I get one solution and another solution, I just add them and that's also a solution. We do this almost without thinking. This is like the Pavlovian response. We see a problem, superposition kind of immediately leaps to mind. But since these equations are nonlinear, I couldn't use superposition of exact solutions even if they could be found, right? So the whole concept of what it means to solve this problem is just different maybe than what where knee-jerk reaction would be. And so in this set of lectures, we're going to proceed by perturbative expansion. And we're going to make an approximation to these equations to make life a little bit easier, that the velocities all come from a potential flow. That is, they are the gradient of some scalar function. And that turns out to be a relatively good approximation on large scales. So this is a plot showing the power spectrum of the density contrast, the divergence of the velocity field, and the curl of the velocity field as a function of scale. And you can see that the curl of the velocity field is very small compared to the density contrast and the divergence. And that's an indication that the velocities are really quite well approximated by a potential flow. And in that case, the velocity is completely specified by its divergence, which I'm going to call theta, standard notation for the velocity divergence. And in that case, I can take those equations and recast them in the following form. So let's just go back and look at these equations. I'm going to take these quadratic terms, the delta V and the VV term, and put them on the right-hand side of the equations and leave these linear terms on the left. And then I'm going to go into Fourier space. So these are just the left-hand side of those equations, now in Fourier space, so with k's everywhere. And then the right-hand side, everywhere you saw a product, in Fourier space, that's a convolution. So I have a velocity times a density becomes a convolution of a velocity and a density. And then I can write the velocity in terms of the velocity divergence by dividing by q squared and then multiplying by vector q. So you can convince yourself that that would be true in Fourier space. And then I have to take the divergence of delta times v, and so I get a k dot q over q squared theta delta. All right, so you can actually just by looking at those original equations, you can work out exactly what this expression is, either in your head on the side of a piece of paper or the back of an envelope. This one's slightly more complicated, but you can go through. This is the velocity piece, and it has this, this sort of structure. And so you can work those out relatively straightforwardly. And then you can say, okay, how would I solve that? I'm now going to go through, and I'm going to first solve the case where I set the right-hand side to 0 here. Then I'm going to take that solution and plug it into the right-hand side and solve the next order and go on iteratively like that.
You want to say something about the gauge?
Oh, yeah, so there's an interesting question about what the hell gauge I'm in when I'm doing this. And I'll answer that question by posing a different question. I'm in the same gauge I'm in when I'm running an n-body simulation. Right? So many people run n-body simulations, and I'm guessing some small fraction of them even know what they're calculating. So what gauge are you in when you're running an n-body simulation? That's the gauge I'm in. And if people want to know the answer later, they can ask me. It's not one of the ones that you probably know off the top of your head unless you do linear perturbation theory more than most of the average people do. The answer is written down in the literature, but it's not advertised, so very few people know that it exists, but nonetheless. So you're in that gauge. Okay. I'm going to go there. All right. So to lowest order in delta and theta, so ignoring the right-hand side, I get the so-called linear solutions in which I start with my initial conditions, and then things just grow by some function of redshift, and a function we can write down quite easily. I factored out this Hubble parameter here. This f function looks like omega matter to the 0.6, but since I've assumed omega matter is 1, this f function is 1, so I could have just replaced this with 1. And this growth factor, in the case that omega matter is 1, is just equal to the scale factor here. And so these equations become quite simple. There's also a decaying mode solution to those equations, which I'm not going to worry about because that will be set to 0 if I'm going to have well-behaved initial conditions. And so from this linear theory, I just get this simple-minded growth where everything grows as A, and I'm going to define delta sub 0 to be equal to the linear theory solution extrapolated all the way to redshift 0. So I'm not claiming that linear theory is necessarily valid at redshift 0, but just as a convenient kind of fiducial redshift at which to evaluate everything, I'm going to scale all these growths out and just work everything here at redshift 0. And then I can develop delta and theta as power series in A. So this will be the nth order term, n running from 1 to infinity, and theta will have the following expansion. And then you can easily convince yourself that the nth order expression can be written in terms of n powers of this linear theory expression. So that's the sense in which it's nth order. It's nth order in this linear theory delta naught. There's a similar expression for theta with this big F replaced by a big G. And I'll write down expressions for what these F's look like. They're just simple dot products of the Q's that go into the arguments of each of these deltas. And so I now have an explicit expression for solving these equations for delta n once I've written down these F's. And these F's come from simple recurrence relations. So what are those recurrence relations? Well, I just go back to my defining equations and you use the following two simple formulae. The time derivative of A is just n times, A to the n is just n times the Hubble parameter. And the time derivative of the Hubble parameter is just h squared, again, assuming omega matter equals 1. Slightly more complicated equations if I have a lambda term or something like that, but not very much. So then if I just go back and plug into those equations, you know, the thing I had that went as d delta d tau gives me n times delta plus theta and so on. Here you get factors of halves and so on, giving you 3 delta plus 2n plus 1 theta is given by this right-hand side, and you can kind of see where these right-hand side terms come from. You know, if I go back and look, you know, there's a k dot q over q squared here. So here's my k dot q over q squared. I have a theta and a delta, and I need to get something that is nth order, and so that is a sum over all of the m's, sort of an n minus mth order delta and an mth order q. So you can just work out all of the ways of doing that. And so these are the equations you end up with. Notice this right-hand side is specified entirely in terms of things which are lower order than the order I'm working at, right? So this is the sense in which I just get a simple recurrence relation that relates the nth order thing to some set of values at n less than n. And so this is a set of simultaneous linear set of equations that I want to solve for delta and theta, so I need to basically do this inversion of this matrix for these right-hand sides. So if I call A and B those mode coupling integrals on the right-hand side, then you can simply rewrite these equations for delta and theta in terms of the following things. And then, of course, these A's and N's involve those sums over the earlier, over the lower order terms. And so you end up with this recurrence relation for F and G in terms of the lower order F's and G's. So there's a little bit of algebra in there that I've skipped over. It's not very hard to do. You can work it out in a couple of pages. And then you can see these, you know, k dot k over k squared terms that came in directly from the structure of the underlying equations and the way in which that nonlinearity occurred. So if you run through that, for example, you can calculate F1 is simple, it's just 1. So you can calculate F2, and it has this particular form. You know, you get lovely numbers like sevenths. Every time you get good prime numbers in an expression, you feel like you've done something quite profound. So here's what the actual structure of those is, and it's just ratios of dot products of these k's. Right? So pretty straightforward. You will note, and it's not immediately obvious, or maybe it's obvious to you, it wasn't obvious to me, but if you actually look at it, this function peaks when the k1 and the k2 are roughly equal, and of course they're both equal to half k, and that turns out to be important. And you'll see why that's important a long time from now. But now I can say that I've told you that, so you should have remembered it, and that way you can feel guilty later on when I tell you it's obvious that this thing peaks at that point. Now, I could make this whole development quite formal if I want to. I'm not going to want to, but let me just tell you roughly how people go about it. I group delta and theta into a 2-component vector. I define eta to be the log of the scale factor, and so that's kind of my time coordinate. So these guys would be constants in linear theory, right? So I've scaled out the simple growth. Then the equations of motion I have look like a time derivative of phi goes as something times phi and something times phi squared. So that's this fact that I have quadratic nonlinearity, of course, with the obvious definitions of omega and gamma here. And I define a power spectrum to be the expectation value of 2 of these phi's, the bispectrum to be 3 of these phi's, and so on. Then I can write down expressions, for example, for the time derivative of p. That's going to be the time derivative of phi times a phi. And so that's going to look like omega times a p. And then one of the derivatives of phi is going to have 2 phi's in it, so I'm going to get terms that go as the bispectrum. And so I'm going to get the derivative of the power spectrum goes as the power spectrum plus the bispectrum. The derivative of the bispectrum goes as the bispectrum plus the next order term, which is known as the trispectrum, and so on and so on. So I get this continuous tower of things that I need to evolve. Now the nice thing is if the initial perturbations are Gaussian, only expectation values that are even in this initial density perturbation survive. So if I take my power spectrum and I say that's delta squared, expectation value, and each of these deltas can be written as delta 1 plus delta 2 plus delta 3, etc., then when I go through here, this is first order in delta, second order, third order, and so I need to get an even number of delta naughts. So the only thing that survive is 1 with 1, 1 with 3, which happens 2 times, 2 with 2, and so on. All of the other terms, things like delta 1, delta 2, vanish because they reduce to delta, 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 right? And that's 0 for a Gaussian. So when you go through and you calculate the power spectrum, you get these relatively simple contributions. And there's a way of organizing this expansion that's basically the same as we do with sort of Feynman diagrams in field theory or expansions in condensed matter physics. There's a diagrammatic shorthand. This nth order delta I write as a line coming in has this kernel f sub n, and then it's in terms of these n delta zeros, right? And if I want to take the ensemble average of something, I take 2 of these linear theory terms, I take their ensemble average by putting a cross between them, and the ensemble average of delta 0 with delta 0 is just the power spectrum, which has these factors in my, my convention of 2 pi's. So for example, if I wanted to calculate the correction to the power spectrum, I'd have these 2 lines. I could take, for example, the piece that went as delta 2. These would be f2 factors, and I can contract this guy with this one, or I can contract it with that one. So there's 2 ways of doing this. I'm going to get 2 p0s, and I'm going to get 2 f2s. And this is the final expression. You get p0 times p0 times these 2 f2s, and there was an expression for f2 that I wrote down for you, and so you can write out that expression. Similarly, I could have sort of a single line here, and I could have 3 lines on the left. Then I'd have to contract 2 of these with each other, and maybe the other one with that other line. That would give me p13. And you just plug that through, and you get the following expressions. And I've just done basically one angle integral in order to get these, and this is the first law of perturbation theory. You can generate truly impressive looking equations that arise from simple angle integrals. This can all be done with recurrence relations, so you can train a numerical algebra package to do this very quickly, and you can look extraordinarily erudite with almost no effort. This is one of the reasons people love perturbation theory, right? So, look, you've got 7s, you've got 158s. This was a hard calculation, right? You can just feel, the power, right? So, so this is one of the wonderful things. I think this is one of the major reasons why people like perturbation theory. You get these expressions, and it's just the same as when you did, when you do combine propagators, when you're doing Feynman diagrams, and you use these Feynman integral tricks to combine these things. You do the angle integral, and you get some god-awful mess, and you think, wow, right? This is basically the same. The same thing happens here. Okay, so you take these expressions, and you can look at them now, and you'll find that at low k, p22 is positive and p13 is negative. And that's the first indication that while the expression looks complicated, all may not be well with the world. That means there's a large cancellation. So something about the way of ordering these terms means that it's possible to start getting 2 large contributions that cancel each other to give you a small contribution. And if you've done a bunch of calculations, that's starting to ring alarm bells in the back of your head that may not have been the most brilliant way of factorizing the problem, right? The other problem is that as you start looking at this, at large k, the total contribution is negative. Now, I'm calculating the square of a quantity. So that answer better be positive, and yet perturbation theory is telling me that the answer is negative. So that tells me, obviously, perturbation theory is breaking down. I can't push this to very high k. Now, maybe it's not surprising that, that I can't do a perturbative expansion when delta is 10. But nonetheless, you have to worry about it a little bit. If you actually look asymptotically, it turns out that both p22 and p13 end up looking like the following. They go as k squared times this sigma squared, which I'll just talk about in just a second, times p linear of k. So I want you to sort of, I'll remind you again of this in just a little while, that asymptotically these corrections end up going as k squared times a number times p, right? And that will become important. But here, the problem is that p22 goes as 1/4 with a plus sign, p13 goes as -1/2, and so the sum of these things goes as -1/4, and so it's negative, and that's bad. But this sigma is this RMS displacement that came up way back when I said what's a good scale of nonlinearity. It's about 10 megaparsecs in the present day universe, and it's just the integral of PL of Q, right? So just integrate the linear theory power spectrum, that gives you a displacement squared, and it's k squared times that, so this thing's dimensionless, right? That is the correction to P. So you can plot this, right? So here's showing delta squared versus k on a linear k-axis, so you're not usually used to seeing this. This is the linear theory result. This is an n-body simulation, so for our purposes this is truth. And then this shows you standard perturbation theory in its traditional form. And you can see that it kind of, the truth exceeds linear theory at large k or at small scales, and perturbation theory does as well. If you want to look at this in more detail, if I just divide out by a smooth curve here to get this plot, so this is power spectrum divided by some kind of smooth fitting function, linear theory gives you this lovely series of wiggles. You see the n-body result there, and then you see perturbation theory, and perturbation theory is clearly doing a better job than linear theory, certainly down here at low k, and then it kind of is overshooting at high k, right? This is a classic thing, and if I kept plotting this all the way out, it will eventually turn over and go negative, right, as we showed asymptotically. The other thing to notice about this, which is kind of cute, is that nonlinear growth causes a suppression of power, sometimes referred to as pre-virialization, in this kind of quasi-linear regime, and that's an interesting result that depends on the local slope of the power spectrum, whether it's going to go up or down, and so that's kind of interesting. And as I mentioned earlier, the expressions for the higher orders are fairly easy to derive if you can use Mathematica. This is actually the work of about an hour. There's one kind of problem with this, is that you can use rotation symmetry to take your nth order integral, so if I'm doing like second order or third order or fourth order, and reduce it down to a mode coupling integral of dimension 3n minus 1. But once n is 3 or 4, that's already kind of an annoyingly large dimension integral. So this is actually best done using Monte Carlo integration, which is a numerical method. So I'm doing this analytic theory numerically. One begins to wonder why not just do an n-body simulation, which is also Monte Carlo integration. It actually turns out it takes about as long to do like fourth and fifth order as it does to run the n-body simulation. But nonetheless, that's okay. Computer time is relatively cheap. So you can do these things. You can go to very, very high orders. Much more worrying is that it's not clear that doing that is gaining you anything. So this is a plot you don't normally see too much of. So again, I'm showing you these things with the broad scale trends divided out. So this is, again, the power spectrum at redshift 0. This is the linear theory result. Red, as before, was the correction to first order in perturbation theory. Black, as before, is the n-body simulation. And blue here is what happens if I go to third order, so the second correction, or third order. And what you can see is, so here's where delta squared is less than 0.4. Here's where the third order correction is less than 3% of the linear. Here's where the third order correction is less than 1% of the linear correction. And what you can see is that even when the third order correction is less than 3% of the linear correction, the first order correction is doing a better job than the second order correction. So this expansion isn't working, right? It's working better down here, but it's not working. Out here you can't really tell. They're both wrong, and they're wrong on opposite sides, so you're not quite clear. But here it's clear that you would have been better off if you'd stopped at second order rather than going on to third order. On the other hand, if I go to redshift 1, now look what happens, right? The first correction is doing what we saw before. It kind of, it's pretty good down in here, and then it starts overshooting, whereas the second correction is now doing much, much better for much, much longer, right? Without doing that third order calculation, you have no idea whether it's going to help. And this is one of the problems with perturbation theory, is there's no rigorous error theory, right? There's no actual convergence criteria for what the hell's going on here, and that's a little bit worrying. So everything I've talked about until now is, of course, just for the mass. You can include bias. I'm not going to spend very much time doing that in Eulerian perturbation theory for reasons that we'll see in just a little while. So obviously, we're not going to be able to take this perturbative approach and deal with something completely nonlinear, like a bound collapsed dark matter halo or something. But we can extend the usual way of thinking about sort of linear bias to say that the density contrast of some object is some expansion in the mass, right, where I just Taylor series expand this, with some coefficients b sub n. So this would be the first order term would be that delta object is b times delta mass. That would be linear bias, and then I could go to nonlinear orders. And then I'm going to take each one of these delta mass terms and expand it to first order in delta naught, second order in delta naught, third order in delta naught, and so on. And so now when I write down expressions for p of k, I have b1 squared times p matter to lowest order, and then I have expressions involving b1 and b2 and so on to higher and higher orders. It's very hard to understand the physical meaning of these terms, right? You can measure them from all kinds of surveys and so on. But if I go to you and I say, aha, I measured it and b2 is minus 0.03, and you go, oh my God, my theory says it's 0.05, what do you do? What do you change? does that mean I ramp up quasar feedback? Do I ramp it down? I mean, you know, it's totally unclear what you're meant to do with these. But this is, in fact, the standard way of including bias in Eulerian perturbation theory. And so, so you often see these terms B sub 1, B sub 2. Now, as I mentioned, in the last decade or so, there's been a real explosion in activity in perturbation theory, and people coming up with all kinds of methods for doing this. And almost all of these methods follow the standard astronomy tradition of misnaming themselves, right? So for those of you who know what a planetary nebulae is, I rest my case. So there's this thing known as renormalized perturbation theory, which does not involve at all the renormalization group. It's a resummation of perturbation theory. In fact, it's what's known as a variant of Dyson-Wiles resummation for those of you who've done particle physics. It's an expansion in order of complexity, right? So this is something that is very, very common in condensed matter physics. When you look at it, you know, the difference between a brilliant condensed matter theorist and an okay condensed matter theorist is that the brilliant one knows how to look at a whole series of terms and decide to keep the first, ninth, and seventh, and none of the others. And you say, how did you know that? And they say, it just looked obvious, right? So you know, you pick a set of terms and you decide that those are the obvious ones to resum, and the other ones are clearly the ones you don't resum, and that's the theory, right? And you know, there's obviously a lot of physical intuition going into this, but it's very hard to codify physical intuition. There's a thing known as closure theory, and this is actually quite a cute way of doing it. Remember, I wrote down an expression for you before that had d by dt of p written in terms of p and b, and then I would write d by dt of the bispectrum in terms of the bispectrum times the trispectrum and so on. So I get this hierarchy of equations that I need to solve, right? So in principle, that doesn't help me because the derivative of p involves p in the next highest order. When I write down the derivative of the next highest order, it involves itself and the next highest order, and so this is, you know, this is never working. So what you do is you need some way to close off this hierarchy of equations, hence the name closure theory. And so in closure theory, you approximate the bispectrum by its leading order expression in standard perturbation theory. Now I get a closed series expressions for the derivative of p in terms of p. There's another variant of closure theory known as time RG theory, or renormalized group and renormalization group perturbation theory. None of these involve the renormalization group, hence the name renormalization group. And these are exactly the same as closure theory, except you set the bispectrum to 0 rather than setting it equal to its SPT value. So there's a whole class of theories in here that are very, very similar. And these are fantastic for models where you have things like massive neutrinos, where the growth rate in linear theory depends on k, which is very hard to deal with in kind of standard perturbation theory, but very easy in these ways of doing it. There's some very nice work on path integral formalism, which basically involves, you know, cracking open your particle physics book, and they show that you can write everything out as a path integral. Perturbative evaluation of that path integral sort of standard, you know, gives standard perturbation theory, and then you can use all these standard tricks in particle physics, like the large n expansion or steepest descents of the 2pi action, etc., and so forth. So all of these methods come up. A lot of these methods, for example, come from fluid mechanics or action turbulence theory. A lot of these methods from particle physics, you can see, you know, where we borrow these ideas from. I want to spend a little bit of time talking about Lagrangian perturbation theory because it's the poor cousin of Eulerian perturbation theory, but I think is kind of an interesting one. Before I do that, let me just show you, roughly speaking, how those other methods I talked about work. So again, my standard plot, p divided by some smooth thing. The points show the n-body results. Red is the standard perturbation theory. And so, you know, here's the large n expansion. This is Lagrangian perturbation theory, which I'm going to talk about a bunch. This is the RGPT I talked about, and time renormalization group perturbation theory. So you can see they're all sort of okay. You know, these guys are undershooting here. These guys are overshooting there. But, you know, that's roughly the degree to which they're working. You don't have to plot just the matter power spectrum. That's the one people mostly plot. But here shows the cross correlation between the density and the velocities. So on very large scales, the density field and the velocity field are almost perfectly correlated. As I go to small scales, like if I was inside a bound dark matter halo, the value of the velocity at some point is almost uncorrelated with the density at that point, right? The particle just happens to be moving through. And so you see this decorrelation as this falls down. Notice the ridiculous scale on here, right? So this is going to keep falling all the way down to the floor. Standard perturbation theory and this time RG approach both predict unphysically that this cross-correlation goes above 1, which is, of course, not possible. RPT and closure theory don't predict the correct fall-off, but at least they don't go above 1, so that's a good thing. Notice, though, that, you know, the scales on which this kind of behavior is happening are actually fairly large. These are Ks of 0.1, 0.2, etc. And so down here, where you might expect perturbation theory to be valid, all of the theories basically agree that the density and the velocity field are extremely highly correlated. So for people who study redshift space distortions, this is fantastic news, right? Because it means that the density field and the velocity field are the same thing, right, to first approximation, and that's an interesting question. How well this holds up when you include galaxies is another interesting question that I won't address right now, but the answer is that it's still pretty good. There's another quantity. This thing is known as the propagator, which is the cross-correlation between the nonlinear field and its initial field normalized by the linear theory result. And so this basically tells you how much you can predict the value of the final field knowing its value in the initial conditions, how much nonlinearity decoheres those fields. And here again, you can see a bunch of these different things and the n-body simulations. And you can see, for example, RPT and LPT both do a pretty good job of describing that fall-off. And this is actually quite important. So if you go and read the literature in perturbation theory, they basically almost trash Lagrangian perturbation theory. And there's a lot of things saying that Lagrangian perturbation theory doesn't work very well. And I think up until 2 or 3 years ago, that was a pretty good summary of what people mostly thought about Lagrangian perturbation theory. But I was really struck by these 2 papers that came out, I guess now almost 2 years ago, by Matsubara, who did a development of this theory, which is really very impressive. This is kind of like reading Lebeck's thesis, where he says, let me think about integration, oh, I'm done. Right? This was kind of a similar thing for Lagrangian perturbation theory. So Lagrangian perturbation theory goes back to the basically late 80s, early 90s, and it's developed in a series of papers that I've written out here. But I want to highlight these 2 by Matsubara, because he has a very nice way of thinking about perturbation theory, which actually becomes extremely powerful for a variety of questions that we're interested in, and as we'll see next lecture in terms of things like baryon acoustic oscillations and so on. So in Lagrangian perturbation theory, what you do is you relate the current, or so-called Eulerian position of some mass element, and I'm going to go about x, to its initial or Lagrangian position q through this displacement field psi. And all of the information is therefore contained in psi. And so when I write down the density perturbation, it's an integral over my initial positions of where I finally ended up, right? So it's a delta function at x minus q plus psi, right? Take off the mean density. So that the density perturbation becomes this integral over delta functions. The Fourier transform of a delta function is simply a plane wave, so you get this simple expression. And then the displacement just grows according to the normal sort of linear theory, or the normal growth, where you have a Hubble drag term and acceleration given by the gradient of a potential evaluated at q plus psi of q. So now what I'm going to do is, rather than sort of expanding density in powers, I'm going to expand psi in powers, and I'm going to write psi as some integral of n powers of delta naught with some different set of couplings, which I'm going to call L rather than F and G, because this is Lagrangian perturbation theory. Okay, so basically doing exactly the same as I did for Eulerian perturbation theory, but doing it in terms of this displacement psi. So these L's are pretty easy to write down. You just take that equation and start Taylor series expansion. The first one is just k over k squared. The second one's a little more complicated. Notice the magic 7. This is looking good already. L3 is quite long, but you can write it down. And k is always the sum of all these p's, so momentum is always conserved at every vertex. And now what I do is I take that expression where I have e to the ik psi, and if I just Taylor series expand in terms of psi, I'm going to regain my series of delta 1 plus delta 2 plus delta 3, etc. So if I look at delta 2, there are 2 ways I can get delta 2. I can have the term where I Taylor series expanded e to the ik psi and got a psi squared and use the linear theory result for psi. Or I can have the term where I expanded e to the ik psi and I got k dot psi, and I used the second order piece for k dot psi, right? And so I get one term that goes as k dot L2 and one piece that goes as k dot L times k dot L1, right? If you take this expression and write it all out, you get F2. And so Lagrangian perturbation theory, Taylor series expanding that exponential, gives you SPT. And this actually refutes many claims in the literature which claim that there's something fundamentally different about them. They're actually the same expansion. And this thing, as you can obviously see, is carefully peaked when K1 and K2 are both the half K. What Matsubara did was extremely clever, and I want to kind of run you through that. He said, look, I can write down my expression for P of K just by writing delta times delta and putting the angled brackets about it. And what I need to calculate is the expectation value of e to the minus ik dot delta psi, where this delta psi is the difference between psi at some point and psi at a different point, right? So if I just expand that exponential and plug it in, that's the normal perturbation theory. So that's what we've just done. But Matsubara wanted to do something different, and it's very clever. It involves this cumulative expansion theorem, which you all just learned. So I can write the expectation value of an exponential in terms of the exponential of the expectation values using the cumulative expansion theorem. And what I'm going to get is an expectation value of various powers of delta psi. So I take each of these k delta psi to the n terms, and I use the binomial theorem to just write these guys out. And if you think about it, there are two kinds of terms. I'll show you an example in a minute, so it'll be a little less vague. But there are two types of terms. Remember, there's a psi q1 and a psi q2, right? So when I take the nth power of that, I'm going to get all kinds of terms. And in one of them, I'm going to have terms that only have psi's at the same point. And I'm going to have some that have psi's at different points. Now, if these 2 points are widely separated, the psi's at different points, this will give me basically the correlation between those 2 points, and that's small. So that I'm going to Taylor series expand out. The ones at the same point, there's no reason why the variance on some scale should be small. Right? When I get to small scales, like they're on top of each other, that could be large. But if they're at the same point, translational invariance tells me that it's independent of position. So I can factor that out of that integral that I had to do. Right? Remember, I have to do this integral d3q, but if it's independent of the actual position, I can factor that out. So let me do a toy model example to show you how this works. Let me imagine that psi was Gaussian, which it won't be when I go to higher orders, but originally it would be. Then e to the psi, by the cumulative correlator theorem, is e to the sigma squared over 2, where this is the variance of psi. So if I take p of k and I need to do this guy, then this exponential for a Gaussian becomes the exponential of this 2-point function. And this 2-point function involving these q's, I can write as those terms at the same point, which I can write as 0, and those terms separated by a distance q. So I'm going to keep this one exponentiated, and I'm going to Taylor series expand that, right? So I have to do this exponential here. So I'm going to have e to the minus a half k squared times this guy, and then e to the minus a half k squared times this, I'm going to Taylor series expand. When I do that, I have to do the Fourier transform of this correlation function, and that gives me a power spectrum. And so I end up with a term that goes as e to the minus k squared sigma squared over 2 times a power spectrum. And if I did this not for a Gaussian theory, but I just kept going to higher and higher order, I can get the p22 term and a version that looks like the p13 term. And I've put a twiddle over this because it's not exactly the same as in SPT. It differs by the fact that, remember, this sigma is an integral of p. So if I were to Taylor series expand this guy, this would have a p in it times a p. But that's exactly what p13 looks like. So what I've done is I've resummed part of p13 into this exponential. And this way of looking at it is actually very nice, because what you can show is this exponential prefactor is identical to that was obtained in the peak background split or in renormalized perturbation theory. And so this one language can now start being used to tie together lots of developments that people had done in different fields. So I've basically taken some subset of these terms that go as p times the integral of p and resummed them up into an exponential, which is very cool. One of the incredibly nice things about this is that I can now, having worked out how to do the matter power spectrum, I can now work out how to do this for bias traces, like peaks in the initial density field or halos or something, and I can do it in redshift space. Redshift space has always been a real problem for perturbation theory. So in redshift space, if I make the plane parallel limit, you can actually do this beyond the plane parallel limit, but let me just make the plane parallel limit, then all I'm doing is I'm saying that the displacement that I'm actually observing in redshift space is equal to what it really was, plus a component due to the velocity, right, the peculiar velocity. And let me write that as some kind of redshift distortion operator, r acting on psi. Then this psi dot, psi n always goes as the growth rate to the nth power, so this psi dot can just be written back in terms of the Hubble constant, so that this redshift space distortion operator is sort of the identity, plus n times the standard, omega to the 0.6 factor, times this tensor, if z hat is the line of sight direction. And so, again, when I leave this zero lag piece exponentiated, I get a factor that goes as k times r, and then I take the dot product, so that gives you this factor, and so you get this expression, k squared 1 plus ff plus 2 mu squared. And then I have a piece that's going to go as the correlation function, which I'm Fourier transforming, and that also has these pieces in it, and this becomes the normal Kaiser expression for redshift space distortion. So you get this nice, straightforward way of looking at those two pieces. The other thing you can do is you can handle bias traces. So remember, I said that delta of mass for x was some integral over these delta functions that the point at q moves by psi to end up at x, right? So now I can say, well, let me give a different weight to different parts depending on their value of the linear theory density field at their original position. So for example, let me imagine f was 0 below some threshold and 1 above it. Right? Then I would be looking at the correlation functions of peaks in the initial density field. So if I think that halos arise from peaks in the initial density field, this would be the halo density field. And so what Matsudaira did, which is very, very clever, he said, well, okay, remember what I do to this now is I Fourier transform this in x, right, to get my plane waves. Let me Fourier transform it in delta as well. So P of k now becomes my Fourier transform, and then I'm going to do 2 more Fourier transforms in delta L so that I have these delta L's up here, and my k dot delta psi. Now, I can massage this expression with exactly the same tricks as I used for the mass, right? Because this is a Gaussian, and this is something I'm expanding. So now I just use the cumulant correlator theorem, collect terms, go through exactly the same series of steps. And so, and you can find these expressions for f. I end up doing these integrals over f, and I get the final expression. And so you end up with the answer. So this is, for example, the redshift space power spectrum of biased halos. It comes from summing these diagrams. There's different kinds of lines here, depending on whether you're inserting a psi or whether you're inserting a delta sublinear. It has the kind of Kaiser form, bias plus f mu squared squared times p linear. This is the standard sort of linear theory redshift space dependence. It has this damping factor that I derived for you 2 slides ago. There's the standard what's known as Zeldovich damping. This was actually well known to people doing n-body simulations. When you initialize an n-body simulation using the Zeldovich approximation, it was well known that if you made the initial particle displacement too large, you ended up with a power spectrum that was smoothed on small scales. You can understand how that happens. The particles kind of shoot past each other and smear out the structure you're looking at. So this was actually very, very well known, and so this has kind of become Zeldovich damping just as a nomenclature. And then you get a whole bunch of terms here that go as mu to the 2n f to the m times some mode coupling integrals that are integral of p times p, right? Some relatively complicated functions. And they go up to E44, so they go up to mu to the 8th times f to the 4. Right? And so you get an expression now for the power spectrum of these biased traces in redshift space that basically follows exactly the same series of steps as you would have done for the mass. So there's no kind of there's extra algebra, but there's no extra ideas involved. And you automatically work out what's the right things to resum. Notice that the damping term does not depend on the bias. That comes out automatically from his method. It's not a priori obvious if you're trying to do it in Nonlinear perturbation theory and so on. So there's lots of nice things about this. I'll leave with this expression up here on the slide. What I want to do in the next lecture is come back and start applying some of these things to see if we can actually do a worked example. I'll do baryon acoustic oscillations, but you could imagine doing a number of other worked examples for seeing if we can apply perturbation theory to cases where I'm working on very large scales, where I expect linear theory to be almost good enough but not quite, and start asking, when these terms are small, how well does it tell me what's actually being seen, what the physics is actually doing, what these small corrections will do. So let me stop here for now.
Do we have questions? Any questions? No? Okay, in that case we'll thank the speaker again. And I have a couple of announcements to make. Please check the for the talks